So I'm going to talk about joint work with Luís Carvalho, João Costa, and José Mourão, all of whom are in the audience. And so my talk will be divided into two parts. In the first part, well, I know that all of you know about multi-layer perceptrons, but I want to recall what they are to give it a spin that makes sense for that will give sense to the second part of the talk. So that, so I'm going to tell you about the multi-layer perceptron architecture and problems that arise when you make infinitely wide multi-layer perceptrons. Then in the second part, I will show how this proposal of Zeta Neural Networks, ZeNNs for short, can circumvent these problems. So I'll present to you three theorems regarding three problems that we identify, and which have been identified previously. It's not just that we identify. And some experiments that give you an idea of how ZeNNs really work to solve some of these problems. Okay, so let's start with one perceptron. So we have a perceptron is a composition of an affine function. That's the first one that appears there, θ2x plus θ1. Then we apply a nonlinear function, which we call the activation, sigma. And then we compose that again with another affine function. Okay, so I'll make here a plot of this function for a specific choice of sigma. So something that looks like that. And if you change the parameters, the theta's in the perceptron, you can move this sideways, you can move it up and down, you can reflect it, and you can rescale it both in the domain and counter domain. But that's all you can do. You can't do nothing else. So you cannot express any function using this, obviously. You cannot even make a function with one maximum using this. But if you add two perceptrons like that, now you have a lot more parameters to play with, and you can adjust the parameters so that you can get a function with one maximum. Okay, or a function with a minimum. You can also do that, but by just multiplying this one by -1. Okay, so that you can do, but with just two perceptrons, you cannot make a function with two maxima. But if you use 4 perceptrons, you can. Here is an example. And you can continue adding the number of perceptrons, and that's a theorem that was alluded to in the previous talk, a universal approximation theorem that says that if the function you choose, the sigma, the activation function, is not a polynomial, then by increasing the number of perceptrons, you can uniformly approximate on compact sets any function that with any precision that you like. Yeah, so it's a denseness theorem in the uniform topology on compact sets. Okay, so pictorially, we depict a perceptron in this way. So you give it an input, that's the leftmost point, if you're looking at it. Then you apply the first affine function. You get to the middle point, where you apply the sigma, the nonlinearity, and then you apply another affine function. Okay, so that's how we pictorially depict a perceptron. And if you want to have n perceptrons, we usually depict them like that. So they eat an input. Here I'm always thinking about just real valued inputs and real valued outputs, just for simplicity. And then you have n perceptrons, and you sum them up to give you an output. But if you are interested in increasing the number of perceptrons, then you should divide by some quantity, or these will diverge. And what is typically done is to divide by the square root of n, and we will see later why that happens. So this is the standard multi-layer perception architecture that is used in applications. It's with only one layer. It's to have these perceptrons summed up and then divided by the square root of n. Okay, why is this problematic? So I now will tell you about the problems that one can identify of when you send n to infinity or when n is very large. So usually at initialization, there are two problems that arise. What do we do at initialization? So we choose the parameters of the perceptrons, so all the perceptrons to be independent and identically distributed. We choose the parameters at random, at initialization, so when we initialize the network. And all perceptrons are chosen to be similar. So the parameters that go into each of them are independent and identically distributed. If you do that, then with probability 1, this perceptron that you initialize this way is not going to converge. So with probability 1 in the space of parameters. So we call this problem A, which is that multilayer perceptrons, as the width goes to infinity, do not converge pointwise. So the lack of pointwise convergence. Problem B is what we call the Gaussian trap, but that this is the name that we gave, but it's been identified several times in the literature. This was already known in the 90s, I think, right? So it says that under these conditions, and independently of the parameter distribution that you pick initially, the central limit theorem tells you that the multilayer perceptrons are going to converge, evaluated at a point, to a random variable which is distributed according to a Gaussian distribution, and the variance is that of the of one of the perceptrons. They are all IID, so one of them. Okay, so this means that you can choose different distributions at initialization. You end up not seeing them. You end up not seeing the difference in the distributions. Only the first two momenta will determine the distribution because they determine the Gaussian. So all the remaining information of the distribution at initialization is lost. You just have the average and the variance of that distribution. All rest is lost. So this tells you that independently of, you will not have parameters to be able to generate different distributions at initialization. Okay, so these are the two problems that I'm going to refer to that MLPs have at initialization in the infinitely wide limit. And now let's talk a little bit about training. So training corresponds to evolving the parameters that go into the perceptrons in order to minimize a loss function. So that's negative gradient flow, to minimize it in the fastest way possible. So I've pictured here a loss function that has two local minima. One of them is smaller than the other. And suppose that you start generating at random parameters to initialize your multilayer perceptron, and that the average lies closer to the local minimum than to the absolute minimum, and that the variance is not too large. And you pick several distributions that way. It doesn't matter which distribution you pick, because initialization is always going to be generated by the same distribution. And you may end up not being able to see the absolute minimum and always flowing to the local minimum. So there is a danger, but that's not one of the problems that we want to identify. So the next problem that happens in training is that there is no feature learning. So here I've depicted a multilayer perceptron with several hidden layers, and now we are going to make the layers go infinitely large. That's what those three dots up and down mean. That suppose we continue this up and down. And this problem, we call it no feature learning. That's how it is referred to in the literature. And that refers to the fact that as you train an infinitely wide multilayer perceptron, only the weights that go into the last layer change during training. All the other layers stay fixed. The weights don't move. That happens in the infinitely wide limit. And that's called no feature learning because there is this intuitive idea that when you have a deep neural network, the first layers are learning features of what you want to learn, of the training data. And then at the last layer only puts the features together to give you the output that you expect it to give. It turns out that in the infinitely wide limit, that doesn't happen. All the layers stay frozen during training, nothing happens, and only the last layer is learning. So that's called no feature learning. And that is a problem in working with very large, very wide multilayer perceptrons. Yes. Before the limit, the weights before the last layer may move, but they move very slowly. And then they end up moving very little. And this leads to another problem that I'll refer later, but we didn't give a letter to it for now. So it's called the difficulty in learning high frequencies. If you think of frequencies as a feature, then you can see how this fits in this problem, but this is really a separate problem. This should really be problem D, a difficulty in learning high frequencies. I'll come back to this. And now let me introduce Zeta Neural Networks and then explain how they fix these problems. Or that they don't suffer from these problems, apparently. They may suffer from others. Hopefully not. Okay, so the idea is to break the symmetry of the perceptrons. It seems it is good to have more perceptrons and to have them even being equal, because that increases the expressivity, as the universal approximation theorem shows. However, it is even better if we let the perceptrons be different. And in fact, we know that in biological organisms, neurons do behave differently, for example. And so what is it that we want to do? The first idea is related to the lack of convergence. So what we are going to do is that we are going to label the perceptrons by J, as I've been doing in the slides before. And in front of each neuron, in order to enforce pointwise convergence, we are going to divide by a factor that goes to infinity as J goes to infinity. 1 over J to the alpha. Alpha is some positive number, okay? The second thing is to explicitly incorporate high frequencies by rescaling the perceptrons from X to JX. So that scales the input up so that we can more easily see high frequencies and model them. And the third is, hope this works. And we can confirm that so we can prove theorems that show that these problems that I've referred to are fixed. So then the idea is to then replace the multilayer perceptrons, which were simply that sum divided by the square root of n, by the sum of the perceptrons rescaled from X to JX, and then divided by J to the alpha. Okay? So that's it. So in its full splendor, the one layer ZeNN is given by this formula. Are there any questions? Well, the universal approximation theorem works for these ones as it worked for the previous ones, because it's just rescaling the inputs. So if you just choose the theta 2j, for example, to be 1 over j times something, then yeah. So these have the same expressivity as standard multilayer perceptrons. It's just that they are initialized in a much more convenient way to learn high frequencies and to have pointwise convergence. Okay, so other questions? Feel free to interrupt me also if questions come up in the middle. Feel free to interrupt me. Okay, so that's the definition of a ZeNN, Zeta Neural Network. The name comes because this resembles the zeta function. So if you regard the zeta function is 1 over j to the alpha as a function of alpha. So it's just from there that the name comes from. Okay, so now let's talk about these problems and how they get circumvented by these ZeNN networks. The first one was the lack of pointwise convergence. And I'm just going to give some hypotheses that I'll use throughout all the theorems that I'll state. So in each individual theorem, these hypotheses can be weakened. But if I put them now in the beginning, I just need to state them once. So I increase the strength of the hypothesis a little bit so that I just need to state them once. Okay, so sigma is going to be continuous, not identically constant, and with at most polynomial growth of order k. Okay, so it cannot grow. So that's the grade of growth. And suppose it's polynomial growth. Why would you ask for something that grows faster? Anyway, seems fair enough. Okay, and then the parameters at initialization are going to be generated again at random through IID distributions. and I'm going to require that they have bounded moments, okay? That the moments are all bounded, okay? So in some theorems, we just need the first moment to be bounded, but I'll just put it like this to be safe. Okay, so the first theorem answers the first question, which is that one regarding pointwise convergence. And indeed, ZeNNs converge uniformly and therefore pointwise. So let alpha be greater than 1 plus k. So that's the extra hypothesis that you need. That tells you the order of growth of alpha. So in fact, alpha needs to be greater than 1 in particular. And that's some point in R at which you are going to evaluate the network. Then with probability 1 in the space of parameters, the ZeNN network is going to converge, evaluated at that point. So
one variable function or general for multivariate function?
it's this is stated for one variable functions, but it's gonna work with multivariate functions. Alpha, we are regarding it as fixed, as an hyperparameter, yes. You want it to be the smallest possible, but so that these theorems are also true. So 1.0001, if the sigma is bounded, it's just a bounded function, then you can put k equal to 0 and alpha greater than 1, but close to 1, it's probably what's best for applications. Okay, other questions? Okay, so that's the first theorem. Now let's tackle the second theorem, which is going to tell us that ZeNNs avoid the Gaussian trap. Let me revisit the Gaussian trap from a slightly different angle that will be more convenient to understanding the statement of the theorem. So recall that the Gaussian distribution has 0 cumulants of order R for R greater than 2. So cumulants are numbers that are in one-to-one with moments, and that as long as the moments of a distribution don't grow too quickly, they completely characterize your distribution, okay? So you can think of them as completely characterizing the distribution amongst distributions whose moments don't grow too quickly. And then the Gaussian distribution is actually the only one amongst those distributions that has 0 cumulants of order greater than 2. Okay, so now let's consider IID perceptrons as we had before. And we are going to denote by lambda R of X the rth cumulant of the perceptron evaluated at X. So we regard the perceptron evaluated at X as a random variable, and I'm going to denote its R cumulant by lambda R of X. Then if you use a multi-layer perceptron with width n and only one layer, it's very easy to compute the rth cumulant of that multi-layer perceptron. And it's given by this formula. It's the rth cumulant of the perceptron divided by n to the power of r over 2 minus 1. This is a computation that it's easy to do, but believe me, I've not put the computation here, but it's relatively easy to check. And as you can see, this goes to 0 if n goes to infinity and r is greater than 2. So indeed, we have proved the Gaussian trap in a way that if you start with a multi-layer perceptron of width n, then all the cumulants of that multi-layer perceptron are going to converge to 0 for order greater than 2. Okay, so the multi-layer perceptron is going to converge to a Gaussian distribution. So what we are going to do to prove that ZeNNs do not suffer from this pathology is to compute a formula for the cumulants of the ZeNN networks and show that that does not go to 0 as n goes to infinity. And remarkably, we were able to do it. It's not so remarkable after you see the computations, but we were surprised that the computations turned out to be doable. So it's remarkable in that sense. So the statement is that for all x, the R cumulant of the ZeNN network is given by this sum. So you sum all the cumulants of the perceptrons evaluated at Jx, and you divide by J to the R alpha. And under reasonably fair assumptions, just like alpha greater than k plus 1, which is the same assumption that we needed for pointwise convergence. This limit as n goes to infinity exists, so that series, that becomes a series and is summable. And it's easy also to see that in general, this does not go to 0. So indeed, the ZeNNs escape the Gaussian trap. So we found this, I mean, we didn't find surprising that they escaped the Gaussian trap, but we find it surprising that we were able to do this computation. And it's a very nice formula for the cumulants. Okay, so that's the Gaussian trap. That also worked out. So now let's go check if feature learning, if we are able to fix feature learning using ZeNNs. So remember that we are using a loss function, and in what follows, I'm going to assume that the loss function is just the square error, okay? And in that setting, training is controlled by a kernel. Calling it, I should have written kernel with inverted commas because it's a kernel that depends on the parameters. So it's not really a kernel in the standard way because it depends on the parameters. That's why it's called k theta, depends on the parameters. And there is a dynamical dichotomy by Yang and Hu that says that either there is feature learning or this kernel is constant, so an actual kernel, and does not depend on the parameters theta. So we can think of having feature learning as having this k theta not be constant. So if we prove that this k theta is not constant, there is feature learning according to this dynamical dichotomy. So you can regard that as a definition of feature learning. The k theta is not constant. And we are able to prove that indeed. So let x and y be points in R. Then there is an open set in the space of parameters, that R for n is the space of parameters, such that the map that from a set of parameters associates this kernel evaluated at 2 points is not constant. And this is true even in the infinite width limit, even if you take the limit n goes to infinity. Okay, so that's the theorems that we have that show that these ZeNNs do avoid these pathologies of multi-layer perceptrons. And then what I want, so how much time do I have? I have a fair amount of time. Yeah, I have plenty of time. We'll go for dinner early. In the next slides, I want to present some experiments that show that ZeNNs can learn high frequencies, which was the remaining problem that we had identified in the beginning. Are there any questions so far? Yes, please.
Define the Euclidean space, right?
Sorry?
Define this in Euclidean space.
Well, the parameters lie in Euclidean space, right? They are real numbers. No, what do you mean by choosing parameters from the Poincaré disk? But the parameters are real numbers. You can, it doesn't, we are regarding the Euclidean space as a set, not a set, not a space with a metric. We are not using the metric in Euclidean space for anything. In the same way, if we pick them from the disk, we would not use the hyperbolic metric for anything. So the metric is irrelevant for these results. So it doesn't matter. It's all the same. You can pick them in a disk if you want. It's not going to affect the results. A disk is a subset of R for n. Yeah, we are not using the Euclidean metric for anything, and in the same way we would not use the hyperbolic metric for anything. That R for n there is just used to parameterize the parameters theta, and also the topologies induced by the Euclidean metric and on the open disk and the hyperbolic metric, the Poincaré metric on the open disk are the same topology. So when I say open set there, it also refers to both those topologies. It is the same thing. There are more questions? Given that I have so much time, please feel free. Okay, so very well. first experimental result is to learn data generated by a function that we picked up. So it's a linear function x plus some sines and some cosines. And we are going to learn this data using a rather appropriately chosen nonlinearity, which is a function sine of x. But you see there is some large frequency there, the 50x. That 50 is a large frequency, right? And we have compared here what we were able to obtain using a multi-layer perceptron architecture and a ZeNN network. And in the left, you have the multi-layer perceptron with 128 perceptrons. On the right is a ZeNN with half of the number of perceptrons, 64, and trained for less time, 5,000 epochs instead of 50,000. And you can see that it fits much better. So the yellow one is the one that we generate, and the green one, or it's actually blue, but the points are green, is the one that is learned. But it gets green on the right because our yellow goes on top of the blue, so it becomes green because it's so very good. I'm joking. Okay, very well. Next task, to learn the temperature time series of the Jena climate data set. This is a famous data set, I think, right? And you see here in green is the experimental points, and in yellow, our fit. Again, this is a ZeNN network now with a lot more perceptrons, 512. The alpha is the same again, because sigma is a sign that's a bounded function, so we can pick kappa k equal to 0. And so alpha just needs to be greater than 1, which shows alpha equal to 1.1 in both cases. And this one is trained for a lot longer time. So the third experiment was to learn two-dimensional data. So here we used a two-dimensional ZeNN, which I've not presented the formulas for in the talk, but we wrote them in the paper. So, I mean, ZeNNs are easy to generalize for multivariate data. And you can do that in a number of ways, which we also discuss. One of them involving the Kolmogorov-Arnold theorem that was mentioned in the previous talk. We call those ZeNNs. Yes, Kolmogorov-Arnold Zeta Networks. ZeNNs. So, but here this is just a standard ZeNN for two-dimensional input data constructed in the most in the most obvious way, but then we use different techniques to generate the images. I don't know with which one it was generated, this image, but in the next slide I'll compare the different ways we used. But you have on the left slide the true image, on the middle one with MLPs, and on the right one, the one using a ZeNN in the first layer. So we just use actually, in all these cases, we used deep networks, but we just used ZeNN layers in the first two layers, sorry. No, first layer. Thank you, João. Just in the first layer. Okay, so here is the one that compares the several ZeNNs that we used. So this is a picture of the peak signal to noise ratio. So the bigger, the better. And it compares different ways of generating ZeNNs in the first layer with another approach to encoding high frequencies, which is the Fourier features technique. So there are two types of Fourier features. One is the standard Fourier features, and the other one is a modification that we made to make the frequencies that are chosen trainable. That's the red one. But you see that the MLP is the worst of them, the multi-layer perceptrons. That's the blue one, the light blue one, sorry. Then there is the standard, so Fourier features, which is pretty good, is up there. I'll point it with my finger. It's this one over here. And the trainable version doesn't perform much better.
You can use the mouse.
I can use the mouse, that's right. Okay. So, and then this yellow one So this is a two-dimensional input. This uses the ZeNN just to detect frequencies in the radial direction when you write things in polar coordinates. So you forget about one of the coordinates. And of course, that has a better performance than the multi-layer perceptron, but it doesn't have as good as a performance as it can have, because you also want to learn frequencies in the angular directions. And then there are the ZeNNs, which are O is for orthogonal ZeNNs, and the random ZeNNs, rando-ZeNN, which are the green ones, which are the best. And the ZeNNs are the ones that use more parameters, so you would probably expect them to generate the best results, but they don't. This is probably related to overparameterization, just to say a keyword. And the random ZeNNs, which generate the initial frequencies at random, do that better and are the ones that perform the better. So these are the green ones over here. Okay, that's all I want to present. Thank you. Oh, sorry. I thought I had a slide with a thank you, but I probably added after 10 minutes. So.
Are there any questions? Maybe Professor Dong wants to. Another question? Or maybe you can discuss this more extensively. You choose that.
It has a range. It's the different. It's not all real numbers, right?
Yes. So if you want to work on the disk, you can just select things from the disk.
In that case,
but the disk is a subset of R4M.
Yeah, but then alpha, the choose will be different, I think.
Sorry? What will be different?
The value of the alpha.
Of the alpha?
Yeah.
No.
What?
Yeah.
With a very small range and.
Yeah. So what you can do is to pick other probability distributions. Yeah. You can pick. So the theta's that I generated is out of a probability distribution in R4, and you can try to see if there are some other. So let me see. Where is that? Okay, so this depends. What this depends on is on the initial probability distribution in R4 that the theta's are generated from, and the statement is that there is. So here we are using a probability distribution that is absolutely continuous with respect to the Lebesgue measure on R4n. What you can try to do is to pick a probability distribution that is not absolutely continuous with respect to the Lebesgue measured in R4n. And then you will have maybe not an open set in R4n. I don't know what the result would be. But that's what you could do to make a different statement. But it's a fairly reasonable assumption to make it absolutely continuous with respect to the Lebesgue measure in R4n.
Another question?
The overfitting, I don't know much about what happens here. Maybe João can add something. Regarding why do the blue ones do not perform as well as it would be? Yeah, I think it ends up, for example, I think it ends up being overpassed by the Fourier features at the end. It goes up quite fast in the beginning, so it learns very well in the beginning, but then it ends up learning very slowly after that.
Maybe following up on Fernando's question, if I go back to the problem with the signs, you cannot overfit. You don't have a noise, for example. So I worry about your networks because they pick up high frequencies. Maybe that they overfit more easily than the MLP because it's going to pick up the noise. So is that?
Yeah. So if there is noise, they could
pick up the noise more easily than an MLP. So that would be a problem.
Yes, but
this is here you are just fitting. Because the problem that you normally want to solve is not fitting.
Yes,
it's generalizing to
Yeah, I understand the concern. I think it's a valid concern. Let me say that what we have that can fix that problem is the convergence factor, because the convergence factor, it's inspired by what happens in harmonic analysis, and it does penalizes high frequencies because you are dividing by 1/j to the alpha. So if you have some noise that is, as for example, here would have frequency 500, it would be divided by 1/500 to the alpha. So that does penalize the noise that may appear. And that comes, I mean, but the inspiration for this convergence factor is, for example, the Riemann-Lebesgue lemma. The Riemann-Lebesgue lemma tells you that when you write the Fourier series of a function, the coefficients, the AJ coefficient, needs to converge to 0. And if your function is C1, it needs to go faster than 1/j.
Experimentally, it would be easy to test. I mean, like you can have your sine function with less points and a bit of noise and see what happens. Yeah.
Yes, we should experimentally maybe try a little bit about. Maybe João can add something to answer that. Yeah.
We just try to learn the linear part. Yeah. So and then you can use regularization and they will learn well. So just an L2 regularization factor. And you'll end up dumping the, they will dump. Sure.
Yeah.
Of course. If you just want to learn a linear function, you will overfit. Yeah.
Because you're using also sine as an activation function. So everything that you make with the sine goes. Yes, this is something to think about. Yeah.
So, Gonçalo,
Yes.
one question. I mean, you see, as you yourself said, this is quite of a, I mean, the theta J couldn't be from a multi-layer perceptron because they're just a rescaled version of that.
Mhm.
So you can see this kind of a regularized MLP. So couldn't, or at least this sounds like that. So couldn't you obtain that as with a penalizing factor, like a kind of regularization, really? As would that be possible? Do you think? Or-
Well, sorry.
so the Zeta N networks that you obtained, I mean, the theta J, they could come from an MLP. I mean, if from a multi-layer perceptron, if you put them by hand.
Mhm.
Yes. So the question is, if you could do some kind of regularization, that you I mean, your Zeta network could be like a regularization of a multi-layer perceptron.
Yes, I think you could say it is a regularized version. Yeah. But I don't know. Is that a question or?
Well, it's a question in the sense that what should be the the penalization functions in the sense that you could.
But this 1/j to the alpha is the penalization that we are using. It serves as a penalization. Well, I'm not sure.
That's right.
In the training.
Yeah.
Yeah.
Exactly.
Yes.
Yeah, that was the point.
Yes, but the regularization, the problem of course, regularizations are very useful. But my feeling is that they very much depend on the problem that you have at hand. For different problems, you should really use different regularizations. And this is something somewhat universal that any function, when you represent it in a series, should satisfy.
Thank you.
There are more questions?
Very nice talk, thank you. So in the sine example where you had all these components kind of adding up, you had this very conveniently chosen activation function, right?
Yes.
What would happen if you pick a standard one like a sigmoid or something like that?
Yeah, it becomes much more difficult to learn it.
Because
But
this
it still beats the multi-layer perceptron. It still beats the multi-layer perceptron, but it becomes much harder to learn it. That's true. So it is very dependent on choosing well the activation function.
Okay, but like in real world data, this is really complicated, no?
Sorry?
Like in real world data?
In real world applications, you need to be careful and experiment with several things.
Right.
Yeah.
Thank you.
I would expect. Maybe I would suggest João also answers this question.
Always to learn high frequencies, you need to choose a good Fourier basis to do that. And in that sense, it's similar to what happens with Fourier features, which I guess, from what I understand, it's the bigger contender in solving this problem, which is a very nice solution, very simple solution. They just generate an embedding, a non-learnable embedding of frequencies, sines and cosines, and then put an MLP on top to choose the frequencies from. Okay. And so, and you need to do this, and you choose sines and cosines, right? So in that sense, you need to have this kind of Fourier basis to detect the frequencies. Maybe there are some other solutions.
Yeah. But actually, this question that they raised here, it's what I think our solution is slightly better than Fourier features, is that we do penalize high frequencies in the convergence factor, and that is better to avoid catching noise.
Thanks for the very nice talk. It might be interesting to explore initialization here. So in deep learning, it's known that where you initialize really matters. And ultimately, when you reach your minima, it's not really that far off. So initialization would be something to explore here. And because of the discussion on regularization, I wonder what might happen if you attempted regularization tactics like dropouts. You randomly switch off certain nodes and see how that affects your learning outcome.
Yes, those are good suggestions. What was the first one? Can you repeat it? I'm sorry. Can you repeat what the first thing that you said? Yeah, just to make sure
this is about initialization. So it's
Yes.
shown in various experiments in early literature in deep learning that that initialization is very important. So it would be interesting to explore, how far are you landing from your initialization in your ZeNN
yes.
as a function of what happens.
Yeah, so actually, I can say something about that already, because the first two theorems that we have are about initialization. And one of them proves that there is pointwise convergence. The fact that there is pointwise convergence tells you that in comparison to the multilayer perceptron architecture, which does not converge pointwise, tells you that whatever we are going to generate is going to be closer to the true minimum than the multilayer perceptrons, because it converges. It gives a well-defined function. The second one is that it avoids the Gaussian trap. So this means that you can play around with the distribution at initialization to obtain different distributions that you are going to generate at initialization for the network. So we usually generate the perceptrons IID, and in multilayer perceptrons, it doesn't matter which IID distribution you put, as long as they have the same average and the same variance, the multilayer perceptron is always gonna give you the same distribution. Here, you're gonna be able to play around with the distribution of the perceptron in order to obtain different distributions at initialization. So you are going to be able to parameterize the space of functions at initialization much better. It becomes a parametric model again. You can say that at initialization. So this is superior to multilayer perceptrons in that matter. Yeah, I hope that I think that answers partially.
If I may add just a comment.
Sure.
So these are two very different issues that are being discussed here. One thing is the issue on frequencies. And for that and for the experiment to consider, we had a small number of frequencies that went up to 50 maybe, but this is not related to the other problem, which is the problem of having 1 billion frequencies, right? So when we are speaking about convergence to infinite, the number of artificial neurons, this means that if you are initializing, it's not important how you initialize. You initialize around some frequency, say, but then you cannot cover higher frequencies than that. So if you are speaking about having 1 million, parameters, then you initialize them around 50, then every time after a certain point, every time you add more parameters to your problem, you are falling into the trap of central limit theorem, which means that your sums over neurons, become integrals over the parameter distribution of IID. And the parameters just disappear. So the more parameters you add, the less the system learns, because the farther away they are from the true minimum. While in our case, because we have this penalizing factor, the new frequencies you add, they, like in convergent harmonic analysis, they have smaller and smaller importance, and they contribute to approximating the function using harmonic analysis. You multiply frequency.